This talk today is reporting on the results of a group project with a number of us here at NC State on the materials genome, looking at nanoparticles and interfaces and lubrication. And I thought, well, I have a thought for the day. It is Earth Day. And if we don't remember anything from the lecture, maybe we'll remember the thought for the day. A couple of years ago, not long ago, I was out running and went by this white car, something like that, and heard this knocking on the inside. And it was actually a child knocking, maybe a young child, 2 years old, trying to get out of the car and calling and loosen the car. And I went over to that bike shop and everybody got involved and they started making these announcements to every store in this shopping center saying, would the person who owns the white car come get their kid or we'll call the police. But everybody got involved. It wasn't all that hot that day, so it wasn't like we had to take a baseball bat. But the thought for the day is, what would you do if your kid was stuck in a car? Would you walk by? Would you ignore it if it's hot? Because your kid is stuck in a hot car. Well, we'll get back to that. The first part of my talk, I'm reporting on the nanodiamond studies that we've done as additives and what they do at the nanometer scale and macroscale, combined in different materials and with different traditional lubricant additives. And then the second part, these are my climate impact estimates. I'm always wondering, okay, we hear people say the friction is reduced by 75%, or we can reduce carbon emissions by so many gigatons. And I like to go through and say, well, what does that mean? What's the impact? How important is that? And so at the end, I'm working through from what this means to carbon reduction, finally to what that means for temperature, climate, global warming increase. So let's see how we got in the situation. Oh, about 100 years ago, the first cars were emerging. There's a 1916 Maxwell Tourer. You can still see them at fairs. And it was sort of a full-time job owning one of these things. This is the owner's manual out of Ken Ludimo's textbook. Pretty much lubricate, lubricate, check engine, change oil, lubricate, full-time job. Well, that just, lots of smoke coming out. 50 years ago, the cars were better. There's a famous report, the Jost report from 1966, that noted that you don't even need anything new. If you just paid attention to tribology, economic savings of 1.3 to 1.6% of the GNP could be had. And that was before computers. Well, that really got a lot of attention, and there was a lot of research on tribology that was triggered by this report. And one of the outcomes of that research was the development of anti-wear additives. Tricresyl phosphate, TCP, is one of them.
Yeah.
And I show here how as you raise the temperature, it has a reaction with iron surfaces, and it forms a very hard protective anti-wear coating. Another additive that was developed at the time was the ZDDP. And here's a coefficient of friction. Well, I think this is a 1980s publication, 83, showing that when this film goes down, the coefficient of friction actually goes up. And that's how little we cared about friction at the time. The energy was cheap, and as long as the machinery didn't self-destruct, that was the big thing. Population was much smaller, but the additives in the oils, in our lubricants, ZDDP, TCP, they're toxins, and they drip out of the automobiles, and then they get washed away into our watersheds and pollute them. And this has just been building up. And we want to get away from them. However, their thin layers are all that keep us from having our cars not work and our airplanes dysfunction. So cars last a lot longer. There's a lot less wear, but they do remain inefficient. So let's take a look here. The typical passenger vehicle, according to a recent, 2012 publication by Holmberg and Erdemer, 100% of the fuel energy going in, you can see where it goes to: exhaust, cooling, frictional losses. The oils limit how hot you can run the engine to increase the Carnot temperature efficiency. But you're only using 21% of that fuel to actually move the car. And this also tells us why, if we increase or reduce friction, let's say we reduce friction in the engine, well, the engine is only accounting for 11.5% of the total consumption. And so we don't get, if we reduce the engine consumption by 10%, we don't increase fuel economy by that much. And interestingly enough, in the 50 years between when Holmberg did the analysis and Jost did the analysis, the percent of the GDP that could be saved by better tribological practice is almost constant. But what has changed, longevity has been pretty much accomplished. We now use many objects until we're bored with them, not until they wear out. But friction has taken over as the main economic factor because of energy increases in price. The two sectors, what we're looking at here is one of these Lawrence Livermore energy flow maps, and they're constantly updating them. We can look at recent ones. We can look at them for every country. What I'm showing here, I don't know if I see the year, but the two sectors that are particularly inefficient are transportation and electricity generation. So all that gray is just energy that is dumped out as heat and wasted heat that we're not actually doing any work with. Transportation is this 21% efficiency, and electricity is pretty bad too. Of course, global warming looms large, and it's Earth Day, so take a look. Here we are in 2020. A couple days ago, I heard that reported that the temperature increase today was about 1.2 degrees above pre-industrial times. Every time we put carbon in the atmosphere, it more or less stays there indefinitely. And so it's just building up. I took a look at when I first started working in this area, how was the carbon building up back then? And March 85, 347.8 parts per million. That was during a recession. And we see it creeping up by a couple parts per million every year. Here it is in March 2019, 20, and 21. Yes, the pandemic has impacted some of that, but we see it just creeps up and up and up. As we put it in, it's not good enough to say, hey, Mom, I cut my carbon in half, because you're still putting it in and it's still creeping up and other people are putting carbon in. I don't think we're going to make the 1.5 degree limit. We focus on this 2 degree here. Maybe models say if we capture around, get to maybe plateau at 500, we might be able to make 2. And I'll point out on these projections also that this is the 2/3 probability. So 1/6 we're way off in the one direction and 1/6 way off in the other. Well, can nanoparticles help? Yes, of course they can. Let me just show you what here for lubricants. What we see as a sliding interface, our vehicle goes from a slow speed at the left, this is the Strybeck curve, where we've added in nanoparticles, over to a high speed. So think of when you're driving really fast and your car starts to hydroplane. The solid contacts have lifted off, and the friction is now dominated just by the viscosity of the liquid. So you'd think, why don't we just use water or electrical repulsion to levitate everything? Something with nice low viscosity. The friction here is going linear in speed, so it's going on back up. Well, that's because sooner or later, the vehicle will come to a stop, or the machinery, and then the weight is 100% supported by solids. So you go back to the F equal mu n solid friction law, where a lot of abrasive wear can take place. And then as the material speeds up, sliding, the liquid starts to take over, bearing the weight, and then it becomes this mixed lubrication regime. So nanoparticles can ideally benefit everywhere. Up here, frequently nanoparticles are charged, and so they can help with the electrical repulsion and lifting. They can cause effective viscosity reductions, even if the actual fluid viscosity has not dropped. The particle reductions can drop. The mid-range here, they can smooth it out and cause it to hydroplane sooner. And at the low end, they can support the solid weight, prevent binding, and even roll. So ideally, they should be quite helpful. Here's one of Olga's publications showing a coefficient of friction in motor oil with and without some of these standard additives. And indeed, a reduction is seen and is very promising. Well, what could possibly go wrong, right? This is great. I'm just going to rattle through all the things that could possibly go wrong. And then the same type of thing when I talk about how wonderful nanoparticles or nanodiamonds can be. Very often someone in the audience will say, well, couldn't this happen and couldn't that happen? Just worries. Well, they could abrade. Now, abrasion of a surface is not necessarily a bad thing. In fact, here it's used as a polishing effect to anchor other materials in magnetorheological systems to actually make a friction go up strongly. They could be incompatible with existing additives. Certainly conceptually, it could all just fall apart, especially something like TCP that is still used heavily in the airplane turbine engines. It's very, very fickle. It doesn't lubricate chrome or nickel. It's very sensitive to how much carbon. And if it's so sensitive to carbon, do I really want to be putting in carbon, nanodiamonds? Just let's see what happens to our airplane. The reaction might get eaten up, that the carbon is reacting with this TCP or other additive and never even make it to the surface. It could cluster or glomulate, filter out, get stuck in your filters, making big particles. It could change your oil viscosity. Am I keeping anybody awake yet at night? It can change the roughness, the whole film that's formed, that is our anti-wear. And I'm constantly asked about the environment. What about breathing them? So there are plenty of things that we worry about. And so that's why we study from a first principles point of view what nanoparticles are doing at the atomic scale and what they're doing in macroscopic test systems. We use a bunch of different devices. Way over here on the right, just a standard MTM ball on disc setup. On the left, we take the ball and put it right on top of a QCM, quartz microbalance, that vibrates back and forth. And we use a bunch of intermediate steps to connect it all together. One we call the Da Vinci, which is just a bunch of little ball bearings pulled on a slider across the top of the QCM and the MTM disc. So a QCM it's about the size of a contact lens. It's a single crystal of quartz with a metal film on it. We apply a voltage and that causes it to vibrate in a transverse shear motion. To look at nanoparticle uptake, the simplest setup is shown here, where it's dipped into a liquid. It could be oil, water, and there's an oscillator on top, and we watch the frequency and amplitude of vibration as we add nanoparticles. So what happens when those nanoparticles go in? Well, we virtually always see a shift in the amplitude of vibration, and we always see as well a shift in the frequency. And these reflect how much mass is being dragged along, the viscosity of the material, whether there's abrasion, whether there's slippage. There's quite a bit going on. And so it takes some modeling to understand it, unless it has a very straightforward response. Nonetheless, these shifts are quite indicative of the ability, as we have found, the ability of a nanosuspension to be lubricating at the macroscopic scale. So after we add them, we see on the top panel, there's a drop in frequency indicating some mass uptake. The middle panel is quite fascinating because the resistance to drag through the fluid has dropped. It can go up or down. And then the lower panel is our work to look at the various combinations of frequency and resistance shifts in order to find what we call the performance factor, something that would indicate performance at the macroscopic scale. But the one to really look at and focus on is this, oh, it's not showing up, the minus 2.5, because it actually got slipperier putting those nanoparticles in, even though nanoparticles increase viscosity of a fluid. So let me take that same fluid and put it in a macroscopic MTM test device with the same material combinations, and we found that there's a particular performance factor, delta R over delta F, that correlates very well with macroscale friction. We believe this is in the mixed lubrication regime. That would give us hope of a prediction for whether something is a good lubricant at the macroscopic scale. And we've tried it and reported it in this case for alumina surfaces. We see one material, the alumina on alumina, looking rather bad, with the iron oxide looking like it should be good from the performance factor point of view. And also the titania looking bad. And that does turn out to be the case when we go and put this and measure the alumina on alumina discs. So there's a beginning here of a way to go about measuring nanoscale properties with some idea of what will happen on the macroscopic scale. This is very new and in development. Well, what about oil? We don't see a lot of slipperiness for some these are nanodiamonds in oil. On gold and nickel, we do see evidence of abrasion. Notice the resistance went up, but the frequency is starting to drift up, which is an indication of some abrasion. What about water? That's a fascinating one because water is not used as a lubricant because its low viscosity usually results in cold welding of the materials at low speed. But if you have nanodiamonds there, that should help. So the first study we looked at was comparing positive and negative surfactants, or not surfactants exactly, the treatment, the surface treatment on the nanodiamonds to prevent them from recombining in the material. And they had very, very different response in the liquid. So these are for negative nanodiamonds in water, or 5, 10, and 15 diameter, and positive nanodiamonds that are nominally 5 nanometer, but they did have some recombining. We see the resistance dropping for the smallest negative nanodiamonds. And measurements and also computer simulations have shown that these negative nanoparticles on metals, which are also generally negatively charged in water, are allowing an interstitial water layer that is not present for these positive nanodiamonds. And that is changing the friction. Don Brenner and group very much leading this simulations, also have performed the simulations of positive, negative, and neutral nanodiamonds. They can do that. They can hold it constant and simply add different surface treatments and examine this. And again, very different frictional properties. So the interfacial properties are controlling the friction at the nanoscale and the macroscale here. We've seen this in the lab for macroscopic MTM measurements of these same systems, that the negative nanodiamonds, we see a reduction in friction. Again, this is in water. For both stainless steel and alumina, and for the stainless steel, the positive nanodiamonds were quite detrimental. The friction skyrocketed and there was a lot of abrasion. So, comment there, watch out for electric fields. We have electric vehicles on the way. Yes, this can be very, very beneficial. But keep in mind, the charge and the interfacial properties have massive impact. Let's now, I'm moving on to what we see when we combine them with conventional additives. We saw a little bit of that in Olga's publication reporting on ZDDP when added to nanodiamonds. Here we heated it up to have the thermal reaction film form on the surface from an oil that had either no nanodiamonds or nanodiamonds, but it also had TCP. So the setup is pretty much the same, except that we have it in an oven of materials that can be heated. We add 5% in advance, and we're not attempting to look for the effect when we add the nanoparticles. We are heating this and watching for that reaction that occurs around 200 degrees to see what will happen. And then we're looking at the properties of the films and doing a lot of AFM and chemical composition, measuring coefficients of friction. And we've published these results, so I won't go at length on every detail. And I'm just going to very quickly mention what we see when these particles are added. Oops, this went the wrong way. The dry friction coefficient slightly went up, but not really a cause for concern. The formation rate of the film that forms at the reaction temperature was about the same, 2.4 nanometers per minute. And the nanodiamonds were definitely embedded in this thermal reaction film. One of the most interesting results is it extended the range of materials where a film would form. TCP, again, can be quite fickle about chemical composition and the need for some type of iron. our best explanation at this point is that there is an abrasion going on that allows the TCP to reach the iron. However, Ashley Martini has also done simulations of the system, and the nanodiamonds are reacting in the fluid phase with TCP. And so what's striking the surface might also be of a different chemical nature and more easily form a film. So again, I invite you to read every detail and look at the 1,000 AFM images, but let me just comment that when we added nanodiamonds into the oil, the film formation temperature increased by 18 degrees C. The reaction was not completely prevented, but it was delayed, not a lot, unless you need that 18 degrees. The nanodiamonds were embedded in the film. They were didn't change the film thickness, and it enhanced the adhesion and stiffness of the film. So many things changed. It changed the roughness. It changed the contact angle of the oil. It enhanced the adhesion. The stiffness, we believe, is a good thing, because when it is struck by a counterface material, it provides more lift back. So with a guarded, despite the fact that everything changed except the film thickness rate, it appears to be overall synergistic and beneficial. Now, let me just comment, probably the most, if it were me wondering about well, there are many things to consider. It might react with the carbon, and this is seen in the computer simulation. So the nanodiamonds coming in, and that TCP is reacting and forming a different substance in the liquid, which then attaches to form the film. And with a guarded, yes, that seems to be a good thing. But it's not like these little nanodiamonds just went in there and played a quiet role. They're very active participants. Now I'm going to just quickly mention the results of our studies where we put the nanodiamonds in with ZDDP. Now here, a reaction film, we weren't so much interested as looking at the reaction film as the tribofilm. So we loaded the system up with some ball bearings, which you can see ball bearings sitting on top of the QCM in the oven. And we examined what would happen and how would these films that form be changed. So again, in the tribofilm phase, the nanodiamonds embed in the film. So they are there. They are not just hanging out in the fluid, making things slippery. They are active partners in the tribofilm and active constituents. And again, I'm not going to go through every data set. I'm not even going through any of them here. But let me just mention, overall, from our research, they appear to be synergistic. We see them embedded in the film. In this case, it did adhere with it was more strongly adhering, but they did increase the film thickness. And they increased the film stiffness. So this has to do with its ability to withstand another surface striking it. Not too much impact on friction. However, if your system lasts longer, and if the system is smoother, it may change the point where the hydrodynamic lubrication sets in. So load bearing for both systems appears to be improved. And although it's not completely eliminating ZDDP, it does seem to potentially allow you to use less, or at least perform improved performance of the system. Now that's the end of part one. I guess I'll just move on to this second part, unless there are some questions. Should I ask questions now, or should I just finish the last 10 minutes?
At the end, all questions at the end.
Okay. All right. Well, when we burn a gallon of gasoline, we put several pounds of carbon dioxide in the atmosphere. If it was leaving behind bags of charcoal briquettes, it would be more impressive because our houses and roads would be full of them. But as it is, goes into the atmosphere, is not detected, not until about 1,000 parts per million. That's where people start to report headaches. We're not quite there where we walk outside and get a headache or inside. Oil consumption increased precipitously with the automobiles becoming viable systems. And what I'm trying to show here is that every time we've added a power source, we use more power. And the same can happen with renewables. We might just keep using everything at plus the renewables. As an example, there is a growing literature about IT. We think that by staying home and telecommuting, our Zoom meeting right now, instead of flying, we're saving carbon. And IT is heavily using electricity, but it might be gobbling up all the renewable electricity. Well, you can read it for your own, but I'm just pointing out, I think this one was published by Greenpeace, that if IT was a country, and this was like 8 years ago or something, it would be the third largest carbon emitter on Earth. So there are sources of carbon in the atmosphere coming from all directions, and models abound. And we can look at them and say, oh, who knows what's going to happen, right? You look at this one, and these are the trajectories of historically what the emissions are, and then going into the future, what the emission might be, and then what the temperature will be, temperature increase in the year 2100. And the different paths, we're at the point, if we want the blue line, we're going to have to start gobbling carbon out of the atmosphere rapidly, about now, yesterday, right? I think 2020 was the last point. So models are there, and we could group them. Take that same picture. Well, we didn't. These are from the climate change planning committees, talking about a goal for what the temperature would be and how many parts per million would be in the atmosphere. And it's cumulative. So you have a certain amount in the atmosphere right now, and it only goes up from there unless we're taking it out. I'll focus on this 2 degrees here, because I think we've blown by 1.5. Maybe we'll reach 2. So let's decide that we wanted to cap it at 2 degrees. I have the units down at the bottom axis there are in gigatons of carbon and gigatons of carbon dioxide, because carbon dioxide is, 3.8, almost 4 times heavier. This is one that catches our attention. The last time we had 400 parts per million was maybe 2 degrees, but the forecast for 2100 is up there at a sea level of 50 meters higher. Here's 2 degrees, here's a 20 meter rise. So I guess we're still okay in North Carolina, but it's like we're going to be beachfront property here. This is serious business that even at these levels, we're going under eventually and slowly. So plans for 2 degrees. There are lots of plans. And The important thing to notice about these plans is that everyone must contribute. There are no ways out without all sorts of contributions from renewables are doing a huge share, but just shifting to renewables will not get us there. Fuel switching is switching to, say, natural gas from carbon to something that is less carbon emitting. Carbon capture, that's getting bigger and bigger. We're going to have to capture it and not let it out there. Let's take a look at efficiency, 40%. That's where our friction falls. And the models that our experts are setting forward are saying that efficiency must count as the largest sector. It doesn't really matter which model I've been looking at. Efficiency means either stopping doing something or doing it with less carbon emissions. Now, maybe I have an error here, but I thought I would see what, if I just did I think I spent 2 minutes on this to prove that everyone can spend 2 minutes. And since this is taped, everyone to eternity can see if I have a math error here. But okay, well, what if everybody's like me, right? Because everybody's like me, right? So I said, well, what am I contributing? So, oh, suppose I drive 15,000 miles per year, and suppose my car gets 30 miles per gallon. And is that 500 gallons per year? Yeah. Okay, now how much carbon is being spewed into the atmosphere by my car? Okay, again, these are the 2-3 minute estimates, but they're fun to do, or maybe alarming. 17,600 kilograms. Now, of the amount that spews into the air, only about half stays there. The rest, about a quarter, goes into the ocean and makes it more acid. A quarter comes back to Earth. These are very rough estimates. Now, how many vehicles are driving around on the Earth right now? I don't know. I could look it up, right? No one remembers anything anymore. Maybe 1 billion. And then I get to 8.8 times 10 to the 12 kilograms per year going into the atmosphere. That's if everybody's driving 15,000. You get the idea. Now we're going to go up to 2,100 and say 80 years worth. How many tons of carbon have gone in the atmosphere? And what I have is if 1 billion people drive like me for 80 years, or my descendants, 700 gigatons. Yeah, I don't like that. That's a big number. It does contribute. Now that's me in 3 minutes. Let's look at, so that's an extra 700 gigatons added if all my numbers are correct. But there are experts who look into this, and Holmberg, Anderson, or Ali Erdemer, they have published extensively this article and a series of follow-ups. And they report for passenger vehicles 210 billion liters of gasoline were used. So that number is 10 times less than my estimate, which means either I made a factor of 10 error along the way, or people are not really driving 1 billion cars, 15,000. But they have added up how much is going on. And not only that, they have added up how much can be saved by friction and reductions and improvements in tribology. So they report in terms of how many gigatons of carbon dioxide. So I went ahead and put their numbers in, and they talk about the time it takes to implement long-term changes to production. You don't just overnight switch from one technology to another. And with that reduction of what's spewing into the atmosphere, I cut it in half because only about half stays there. And it comes out to be about preventing 0.25 degrees of global warming if this realistic numbers and tribology were implemented. So it could avoid 0.25 and 3 degrees C. In some sense, many have been resigned to say by 2100, maybe we can do 3. It's slipping. Now, what about impact for passenger vehicles? I just want to go back to this breakdown. This was for a passenger vehicle. And what we don't know is what is the breakdown for a wind turbine generator? What is the breakdown for a tank, military vehicles, construction vehicles? To the extent that the friction in their engines and transmissions are the main source of energy loss, then frictional improvement will take on a much larger factor as well, and not just be 3% as improvements are made. The transition will be slower for freight and planes. And time is up, so I'm just going to finish by making a few key points. First, about nanodiamonds. They have great potential for contributing to energy efficiency and also new technologies, allowing technologies to be developed that could not be successful or viable based on some of the older approaches. And we're not seeing massive friction reduction. We're seeing almost more of an effect of a polishing effect and key surface chemical treatments causing quite a improvement. As far as energy efficiency, it is expected to contribute 40%, and friction is about 1/3 of that. They say it's not too late. All sectors are needed. So if we go back to our child trapped in the car, we don't need to get out the baseball bats. We need to start working now. Everybody needs to work, and the problem can be solved. Thank you. That's it.